No questions about lab? Question?
Are we meeting downstairs or upstairs?
I think the syllabus says downstairs. Is that right?
Which is the classroom on that?
Same classroom we met in last time. Hopefully it'll be available. We'll be on that side over there. Other questions? Any questions about material from last time?
There's a question of lab. Are we turning in like our pre-lab and stuff we usually for
No. No, you're prepared to work in lab, you have a pre-lab, and you're prepared to work in lab. If you're asked to turn it in, you can turn it in, right? Mm-hmm. Okay. Other questions? Yes?
On the yellow sheet for the daily questions for test 1, are we supposed to know how to do number 2 yet? Or are we going to
Low structure?
Right, of the organic compounds?
We're getting there. You should...
I've attempted, but I can't get it, so I just want to know if I'm behind or if we're going to go over that.
No. Again, these are not like strictly day 1, day 2, because sometimes I vary and sometimes... But in general, along the way, by the time we're halfway through, after 5 lectures, you should pretty much be able to answer at least the first 3 or 4.
Okay.
Then the ones on the back are going to be more towards, as we get closer to the test. Last thing we'll cover is like question 12 and 13. So it's roughly in order of how we're going, but not exactly. I think you're okay. We'll see a couple of things today, then up to the larger structures. We did some small structures. Okay, larger structures. One thing, okay, let's get started. One thing with larger structures is to know your building blocks. Okay? You can put together structures, not atom at a time, but functional group at a time. All right? Get to bigger structures. Of course, you just need to know your functional groups. Names of them, they need to be spelled correctly. Hydrocarbons, alkanes, just all saturated. Okay, saturated hydrocarbon. That's a condensed structure. Bonds are not shown out. Okay, alkane nomenclature covered by video only. You have that handout and the video. Alkenes, enes, have the double bond, carbon-carbon double bond. Has to have 2 carbons to be an alkene, carbon-carbon double bond. If it has a carbon-carbon triple bond, it's called an alkyne. Okay? We'll see these lots as we go along. This terminology will become commonplace. An aromatic compound. What's the definition of an aromatic compound? Right there. Benzene ring is your granddaddy of aromatic compounds. 6-membered ring, 3 pi bonds, 4 degrees of unsaturation. Benzene. Okay? Then you can have substituents on the benzene. Instead of hydrogens, you can have other things, including large things. It can be a component of a large molecule. Okay? Like with Lipitor or Prozac. All those up there are hydrocarbons, just hydrogen and carbon. Lots of types of aromatic compounds. In Organic 2, you'll look at aromatic compounds in particular. The definition is over there. We'll soon start looking at hybridization and understand p orbitals a little bit more. Okay, compounds with a CZ bond. You don't see Z too often. A lot of times you'll see X. X is often halogen, but sometimes it can be more generic. Basically, some type of heteroatom, carbon heteroatom. Something other than carbon and hydrogen. Like maybe carbon and halogen. R group, what is R? What is R? It's not up there. There's no R on the periodic table. R is another generic. R is generic for just a carbon group. It can be 1 carbon or it can be 36 carbons. R means just carbon group. Okay? Very often, it's often saturated, but it doesn't have to be. Carbon bonded to a halogen. X is often halogen. Sometimes people use X for anything. For example, carbon chlorine or carbon bromine here. Okay, carbon bonded to the bromine. You got to get used to this type of stuff. The bromine is not bonded to an H. Those 3 H's are on the left side of the carbon as 3 bonds. That's just shown condensed. You got to get used to that. There's a multitude of ways to show compounds. Every time you see it, you got to make, okay, how are they showing it here? Okay. Alkyl versus aryl. Alkyl, alk. Typically it comes from alkane. Alkane, saturated typically, even though it has the Y. If it's got an aromatic ring, it's known as aryl. So that's an alkyl bromide. This is an aryl chloride. Alcohols, carbon bonded to an OH. Simplest would be methanol, one carbon bonded to an OH. We put together a Lewis structure for this last time. On the far right side, there's a little bit of other nomenclature. Nomenclature meaning naming. This comes out of the Smith book. These can vary. Halo group. Some people call it halides. You got to be careful because the IDE ending means anion, of course. You know that. It's not an anion. It's not a bromide. But sometimes people will say that. It's not strictly correct. Alcohol has the hydroxy group. Okay? So that's an oxygen bonded to one carbon. OH. Oxygen bonded to two carbons is an ether. Okay? The OR group is called an alkoxy group. Hydrogen oxy, shortened to hydroxy. Alkyl oxy, because our group is what? Alkyl. Alkyloxy, alkoxy. Just shortened. All right. Amines. This is where carbon is bonded to one nitrogen. We're going to clarify this because the nitrogen is just, I call simple. We'll see nitrogen bonded to something else makes it a different group. Now with the amines, if the nitrogen is bonded to two carbons, it's still an amine. Where with oxygen bonded to two carbons, it's a different name. With nitrogen functional groups, we use the primary, secondary, tertiary distinction. The nitrogen is bonded to one carbon, it's called a primary amine. If it's bonded to two, it's a secondary. If it's bonded to three, it's tertiary. This being the number of carbons that the nitrogen is bonded to. This nitrogen could just be bonded to three methyl groups as opposed to one. That would be a tertiary amine. We will see examples. NH2 group called an amino group. Just about any saturated nitrogen is going to be called an amino group. Thiols. The thiol and sulfide are analogous to the alcohol and ether. Carbon bonding to one oxygen, carbon bonding to one sulfur. Just like an alcohol, it's called a thiol. Thio is often a precursor to sulfur. SH group called a mercaptan. It says mercapto or mercaptan, AN. Mercaptan, very common. Sulfide is analogous to an ether. Oxygen bonded to two carbons. Sulfur bonded to two carbons. Sulfide. Sometimes called a thioether. Well, it's analogous to an ether. You'll probably never hear that group or see that name ever again. Very uncommon to use that. Mercaptan is often stated. Sometimes you hear mercaptans are very smelly. Thiols are very smelly. They put a mercaptan in natural gas so you can smell it when there's a leak, because otherwise natural gas has no smell. You would not know it's leaking. Next table, these are functional groups that contain the C double bond O group, which is called a carbonyl group. Some people say carbonyl. I don't, I say carbonyl. Carbonyl, very common. But carbonyl is not a functional group. Carbonyl is a feature of different functional groups, kind of a sub-feature, okay? All right, carbonyl. All these have the carbonyl. Let's look at what's on each side of the carbon. It can have two other bonds. Carbon on one side, H on the other, such as that. That's an aldehyde. R groups on both sides. It's called a ketone. These are just examples. This here is acetone, which you wash your glassware with. Carbon group on one side, OH on the other, is a carboxylic acid. Okay? No, you would not call this a hydroxyl group. Usually not. You might get away with that, but not strictly correct. When the hydroxyl group is bound to a carbonyl, it now becomes sort of a different functional group. It's a carboxylic acid. You usually refer to the entire group as a carboxy group or carboxyl. YL, a little bit more common. If I was going to point you say to the OH, I'd probably say the OH group of the carboxyl group. I probably would not say the hydroxyl group of the carboxyl group. That's a little, hydroxyl is an alcohol to me. Esters, carbon on one side, O carbon on the other. That's basically where we put a carbon group on this oxygen now. It becomes an ester. The entire thing is an ester here. Here, excluding the R groups. Okay? Then we say that's a methyl ester. Because the methyl is what's been added to the carboxyl. Carbon on one side, nitrogen on the other is an amide. The long name is carboxamide. By the way, some people say amide. I say amide. Some people say amide. I don't say amide. I say amide. Some people actually say amide. Okay, I call it amide. The long name, though, is, I do say a little bit different here. I carboxamide. Or sometimes maybe you hear carboxamide. I'd say carboxamide. Carboxamide is the long name, usually shortened to amide. Carbox because it comes from the carbonyl. It has the carbonyl. If this was an OH, it would be a carboxyl. So we call it a carboxamide now. Amide for short. Again, with your nitrogens, we do the primary, secondary, tertiary. It's got to have one carbon to be an amide. Okay, it's got to be at least primary. If you start putting R groups here, it's still an amide, you just call it secondary or tertiary, depending on how many total R groups you have. Where again, if you put an R group on the oxygen of an acid, carboxylic acid, it becomes a different name. It becomes an ester. By the way, your carboxylic acid is the only acidic functional group on the page. That's why it's called an acid. Okay? In terms of organic, there can be some organic sulfonic acids, which would be more acidic. Carboxylic acid is the most acidic standard functional group until you start looking at some unique ones. Acid chloride, this is instead of, you got the R carbonyl. Why is it called acid chloride? It's not acidic, at least not in the molecule itself is not. In practice it is. Instead of an OH or an OR or a nitrogen, got a chlorine. It's called an acid chloride because it's typically made from the acid. You take the acid and you convert it to this, and that's why it's called an acid chloride. And I'm going to have to look down, guys. I can't look at you too much. Why just chlorine? Because these are very unique, and the chlorine is just the most common. You rarely will see an acid bromide or an acid iodide. They're just very rare. The acid chlorides are most common. Organic 2, you'll look at those in detail. Sometimes more appropriately called an acyl chloride. ACYL. Acyl chloride. You'll see that in organic 2. A couple others from this list. My list came from a Smith textbook. A couple that should be on here that are not. Nitrile. Nitrile is carbon triple bond N. Carbon triple bond C would be an alkyne. Nitrile. Example here. A lot of times we don't show the triple bond N or the lone pair on the nitrogen. Just condense. Nitrile. The group itself, you can call them nitrile or cyano group. Sulfonamide. It's actually another amide. But this is where you got the SO2, which is called a sulfone. And with the nitrogen on it, it's called a sulfonamide. Just shorten that up a little bit. Sulfonamide. It's different from the carboxamide. The carboxamide has the carbonyl group. We shorten that one to amide. You would never shorten this one to amide, because if you just say amide, that means you're referring to that one there. Long name, sulfonamide. Okay, sulfonamide here. Entire functional group is your sulfonamide. This one is probably on hardly any of your textbooks, but it's super common in drugs. Okay, that's why I want you to know this one. All right. Primary, secondary, tertiary. So this is 2 others to know. Let's look just a couple of examples to point these out. We got this amine. Nitrogen bonded to plain carbons. What type of amine is that? What types do we have? Secondary is bonded to 2 carbons, right? It's a secondary amine. Bonded to 2 carbons, so it's secondary. Just a little more information there. Alcohol, yeah. Plain carbon OH. Hydroxy group, it's an alcohol functional group. Ether, oxygen bonded to 2 carbons. It can be an aromatic carbon. It's okay, aromatic ring. Amide, primary amide. Aromatic ring, there's a couple other here to note. This amide. Okay, the entire thing here is an amide. When nitrogen is bonded to a carbonyl, it's an amide. No carbonyl, so this isn't just the plain amine. Sulfide, or aka thioether, alcohol, tertiary amine, secondary amide. Okay. Does that say anything over there? Tertiary amine. A couple others to know. When the OH is bonded to a benzene ring like this, it's a special type of alcohol. It's called a phenol. OL. The OL ending indicating alcohol. But you always want to call this a phenol. By the way, a benzene ring is sometimes called a phenyl ring. So that's where the phenol comes from. The phenyl alcohol, phenol. Where this OH is not bonded to an aromatic. Just plain alcohol, but that's a phenol. Also, we have anilines. If an amine is bonded to an aromatic ring, it's called an aniline. More appropriate name. Because phenols and anilines do have different reactivity, different properties than alcohols and amines. Okay, for me, the handout is the drug sheet. Lots of questions about those drugs, formulas, functional groups, DUS, et cetera, et cetera. Okay. Of course, your textbook is going to have introduction to functional groups and all this material too, and basic questions, practice questions. Any questions about functional groups? Flashcards are a great way to learn your functional groups. Name on one side, structure on the other, something like that, whatever you think is best. What is that functional group? Ooh, I can't remember. Oh yeah, ether. Okay. Anybody not get a pink handout in lab? Somebody got my copy, which was pink on front and white in the back, had a blue mark at the top. Anybody get my copy? Right in there. Okay, let's talk about a little functional groups. The question that was brought up earlier. Functional groups, instead of building structures by atoms, you build them by functional groups. Okay? Maybe you put down an ester. And you know you got the carbonyl and the O on the R's, and you already got something you can put down real quick. I made a comment here. Use your knowledge of functional groups and DUS to help draw a compound from a formula. For example, if given C7H6O2, okay, instead of doing this carbon, carbon, carbon like we did, I did something very systematic last week, small molecules. Once you get comfortable, you're going to be able to do structures quickly. But at the beginning, the systematic approach, I think, is very important because you see the detail of what we're thinking. But if you have 50 carbons, you ain't got time to put every little carbon together. And you're going to want to start using line bonds, okay? And so C7H6O2, first off, how many DUS is this? Ignore oxygen, 4 to 16, missing 10, 5, yeah, who said? Yeah, 5, okay. Well, I mean, well, how about this? There's 6 carbons right there, benzene ring. We need 2 oxygens. How many DUS is this? 4. We need 1 more DUS in our structure. Okay? 2 oxygens. You know any functional groups that have 2 oxygens, or even 1?
Carboxyl. Carboxyl.
Or carboxylic acid? Okay. Or an alcohol would have 1. Do you want to draw an amide? No, an amide has a nitrogen. This has no nitrogen. So, but, you know, you could draw, how many carbons we got? 7? 6? 7? There you go. I know that's right. I bet you a steak dinner that's got the right number of hydrogens. Because we said 5 DUS. Does my structure have 5 DUS? Yes, it does. Does it have 7 carbons? Then the H's are right. And does it have 2 oxygens? There you go. I put together a structure. I didn't do it carbon at a time. I used sort of functional group knowledge and DUS. Okay? That's what I'm kind of talking about there with, you know, your functional, there's your building blocks and line bond, and, okay? Start thinking about that. Closer look at covalent bonding, hybridization, geometry. Okay. Methane, CH4. Let's look at it a little closer. Okay, we may have drawn this last time like this. Methane. It's an alkane. It's a saturated hydrocarbon. precursor meth, 1 carbon, ane, methane. Okay. Of course, we can also show it like this. This would be just condensed formula in this case. But what about the bond angles and the types of bonds and bond strengths? That's bond lengths. That's what we need to talk about now. That all comes from the discussion of hybridization. Ground state configuration for carbon. We drew it before, we'll draw it one time. We'll always refer to that as a starting point. What do we have? 2s, and then the 2p. I left a little gap here, but okay, in terms of energy, yeah. We got the 1s, but that's not valence, just the valence ground state. We have what? 1, 2, 3, 4 ground state, yeah? What do we need to do? We need 4 more electrons. 2 here, 1 there, 4 more electrons, we can get a filled outer shell. But look at this. If we brought in other electrons by bonding, we would put 2 here. I don't know what this would be. If you brought in 2, don't do this. If you brought in 2 from another atom, maybe we can make 2 bonds there. And what would this be? This is not bonding to the carbon. We got to team up with a carbon electron. Also, this looks like a carbon lone pair. Does carbon have a lone pair? No. This is not good. You're going to have a tough time getting the bonding arrangement from ground state. What do we know about the true nature of these 4 bonds? We know they're all identical. You can determine this. We don't have time to talk about how and why. 4 identical bonds. We also know there's no lone pair. We know that from analysis. How do you get 4 identical bonds from that over there? You don't. Carbon typically bonds in a hybridized state. I mean, it's a fancy word for mixed. We're going to mix these orbitals and make new orbitals. Largely based on the math. The theory begins with a lot of math. But it also matches the observations, the data we know. All right, so let's look at this. Instead of bonding like that, okay, questions we need to ask here. How many electron regions around this carbon? 4. 4 bonding regions. How are 4 regions best spread out? If I brought 4 balloons in here and tied them together at the little tie knots, how would they spread out? They would spread out in a tetrahedral manner. Yes, this is nature. Okay? These are important starting points. Basically 4 regions, we need 4 hybrid orbitals. Okay? We're going to get 4 hybrids here. 4 identical hybrids. How do we get these? We combine these 4. If you combine 4, you get 4. You only get 4 by combining 4. We have to combine all 4. I'll say we're going to put these in the blender. 3 scoops of p orbitals, 1 scoop of s. Put it in the blender, blend it up, and now let's pull out 4 identical orbitals. 4 identical orbitals are going to have energy somewhere between those. That's kind of in between those. What are we going to call these? They're no longer called P, they're no longer called S. We're going to call them sp3 orbitals. This is 4 sp3 orbitals. From mixing that, again, a lot of based on math. What do these orbitals look like? Well, sort of a blend of these 2, but we have phase differences. I'm not going to try to combine 4. That's very difficult to do. I'm going to just combine 2. There's a nucleus there. Let's take an S and a P and sort of combine them. The S has 1 phase. The P has opposite phases. Over here, the S phase matches the p phase. This is interacting constructively. And so we end up with like two waves building on each other. And we end up with something long and short, somewhere in between. All right? Something like this. On this side, we have destructive interaction. So it cancels it out, sort of like two waves canceling out. On this side, we end up with something like this. Okay, when these are sort of mathematically combined. And this is going to be more like a hybrid orbital. We combine an S and a P. And so this would be called an sp hybrid. This is the back lobe. Back lobe is always there, but we will never talk about it. Until we get over to test 3, we might mention it. Usually the back lobe is not shown. And when I start drawing orbitals more again, we will not show the back lobe. Okay? And so this is really the orbitals over here, the orbital side. This will vary depending on exactly what you combine. We will see how it varies once we move along. Each one of these looks like this. We got 4 of them, 4 identical ones. Now we put the valence electrons here of carbon. Now we're ready to make 4 identical bonds. We can bring in, okay, remember how we did last week? We had 4 round, don't redraw it, 4 round. We brought in an H with its electron, made a bond, yeah? That's what we can do. We can bring in the H. Instead of X, I'm going to call it H. One electron from carbon, 1 electron from H teaming up to make a CH bond. But we can do this 4 identical times. And we can end up with 4 identical bonds using our 4 hybrid orbitals. And that's the state that the carbon bonds in. That's the theory, but it's also supported by our evidence. Let's look at the carbon. Tetrahedral. Let's draw that. We got, let's see if we want to put a carbon here. Carbon. Tetrahedral. 2 in the plane. 1 forward. And 1 back. Now this may strictly, should have been drawn a little bit down. Tetrahedral, right? Two in the plane. Straight up in the board. Straight that way on the board. But this one is coming off the board towards you. We show that with a bolded. Now it's not going to be exactly like this. I mean, I can't draw this straight out. Okay? You have to see that it's coming out, bolded. And as it comes closer to you, it gets bigger. Pretend like the board's here. These 2 are drawn on the board, that one's drawn towards you. This one has to be drawn back. And we do that with the dashed. And it gets smaller as it's going away from you. Typical tetrahedral. What you have is fine. It might have looked a little bit better if I had drawn this a little bit sort of like this. But we're not going to take time to get it exactly right every time we draw it. All right? This is how the orbitals are spread out. We know that as a bond, but let's make it an orbital. Let's here. Boom. This is supposed to be that. Don't worry about the variation in how I drew it. Orbitals for now. The 4 orbitals are spread out in a tetrahedral manner there. What's on the end of each orbital? It's making a bond to the H. What type of orbital is the H using? H with one electron. What type of orbital is that one electron in?
Yes.
It's in an S, one S. Only one orbital. It's not hybridized. It's just a plain S orbital. This is interacting with an S orbital. Okay? Like this. Maybe erase right here. Carbon, this is your H. All right? And then how do we want to do this? One from carbon and one from H. We could draw another H, or maybe do it as an X here. And right there is where the magic's going on. Two orbitals are interacting, one electron in each orbital, to make a covalent bond. And at that point, again, the discussion could go on for the whole semester, just what is right there in that little bond. But simplistically, we know a covalent bond is two electrons interacting. There's also, it's two orbitals interacting, because electrons are in orbitals. What type of orbitals are interacting? This would be a 1s. I'm not going to put the shell over here, but what is this? That's an sp3 orbital interacting with the s orbital. Repeat that 4 times with 4 identical bonds. And your bonds end up being tetrahedral. And so the correct way to draw this would be, I'm just going to call that carbon, right? What we end up with is this here. So we know what's going on with this dash. We can explain that there, like we did there. Bond angles. What type of bond angle do we expect? HCH bond angle. 109.5. Basic tetrahedral bond angles. You can deviate from that. For me, we will never deviate from that. Tetrahedral is 109.5. The way I drew it up here, what was the bond angle? From 9th grade geometry.
90.
It looks like 90 degrees. Wrong. Okay? It's not 90 degrees. It's an incorrect representation. That's just how we drew it last week. We weren't worried about bond angles, etc. Tetrahedral. Because what's better? These are electrons. Electrons do want to spread out. Do they have more room here or here? They have more room here when we go 3D. And so they spread out that way. Question?
If you were drawing like the sulfur compound with the lone pair, you would still have the bond angle be like 109.5 or just less?
I would not think about sulfur too much. It could be quite an exception. Unless it looks like a standard oxygen. If it looks like a standard oxygen, then it's the same as oxygen. If it's an expanded octet, why is it able to expand? Because it has d orbitals. We're not going to say anything about d orbitals. If you start doing hybridization with d orbitals, it's more complex and different. We're not doing any d orbital hybridization. Only S and P. What do we say? One thing, probably sigma bonds can rotate. If this is carbon with 4 H's, sigma bond can rotate. By the way, what is a sigma bond? That's what we need here. Sigma bond. What is a sigma bond? Sigma bond is head-to-head overlap of orbitals. Okay? Head-to-head. Here we go. Just made a sigma bond. Head-to-head. All right? We can rotate. Well, maybe not. That's the opposite of rotating. We just broke the bond. But in real life, sigma bonds can rotate. There we go. See? Still bonded, but it's rotating. All right? Still bonded. First example was the opposite, where we tried to rotate and we broke the bond. That was not right. Now, in other cases, when we get to pi bonds, the first example will happen. If you try to rotate a pi bond, it's going to break. And thus it doesn't happen unless you put in lots of energy or... okay. What else can we say about methane? Sigma bonds can rotate. That's all we said. Just need to define what a sigma bond is. Next, ethene. F, 2 carbons, ene. Sounds like an alkene, 2 carbon alkene. Questions while I'm erasing? Carbon-carbon double bond. Carbon makes 4 bonds, so we also need 2 H's there. There's a good structure. Ethene. Slang name that was ethylene. It's an L-Y, ethylene. Okay, let's look at the carbon. Both carbons are going to be identical. What we say about one will apply for the other. We began with the same types of questions. How many electron regions around this carbon? 3. Single bond, double bond. A double bond is one region that way. 3 regions. 3 regions is what? Not tetrahedral. Tetrahedral is 4 regions. 3 is trigonal planar. Because if I tie 3 balloons together, how would they spread out? They would spread out trigonal planar. Okay? Each time you have a balloon party, tie 3 balloons together and watch them spread out in the right way. All right? We need 3 regions. Your regions come from your hybrids. With sp3, how many hybrids did we have? 4. Okay? Just opposite thinking. If we need 3 regions, how many hybrids do we need? 3. Your regions set your geometry. Your hybrids set your geometry. Your geometry is set by hybrids. 3, you need 3. 3 is going to be boom, boom, boom. Okay? We said this, if you combine 4, you get 4. How many do we need to combine to get 3? Very good. We need to combine 3 to get 3. The 3 we're going to combine are, we're always going to combine this. We're going to combine these 3, and we're going to get those new hybrids. 3 go into the blender. 3 scoops of ice cream into the blender, we get to pull 3 new scoops of ice cream out, but now they're blended. We didn't put this in the blender. So the p orbital is still there. Okay? What do you want to call these? Well, what went into the blender? 1 s and 2 p's. So we're going to call these sp2s. This is 3 sp2 orbitals, hybrid orbitals. Each one is called an sp2 orbital. But that's what went into the blender. Okay? Now, for this carbon, we have electrons here and here. Now we're ready to make the appropriate bonds. What do you see this carbon doing? We have a sigma bond to H. How do you know it's a sigma bond? Because single bonds are sigma bonds. And sigma bonds are made using what type of orbitals? Hybrids. All right? sp3, everything was a hybrid. That's the type of bond. Okay? Now I'm using a hybrid to make a sigma bond. I got another sigma bond to H. And then you actually have the double bond. The double bond is 1 sigma to carbon, and then the other is here. All right? This is your double bond. The double bond is a sigma to carbon, and what is this going? What type of orbital or bond will that be? What type of orbital are we using to make that bond? P orbital. When you use p orbitals to make bonds, it's going to be called a pi bond. And the p orbitals do not interact head to head, but side to side. Okay? Let's see if we can draw this out. We got this 1 carbon. We have 3 hybrids. We're going to have 3 hybrids in a trigonal planar. Let's put 1 here. Let's put 1 here. And let's put 1 here. Back lobe, back lobe, back lobe. No, we're not going to do that. That'll make it too cumbersome. We know hybrids have back lobes though, right? How are these 3 hybrids spread out? Trigonal planar. 3, all on the plane of the board. Not forward or back, planar, plane of the board. All right? Each one of these is called an sp2. Yeah? What is this one interacting with? H. Okay? I like to do this kind of quickly. Just like before. One electron from the carbon, one electron from the H. Okay, maybe put them in here. The magic there, the covalent bond. Sigma bond, that is head-to-head. 2 sigma bonds. What is this making a sigma bond to?
Carbon.
The other carbon. It's the exact same over here. Okay? There's the magic. And I'm going to call this over here, well, we just did there. Okay? Exact same. I may not finish that up. Let's finish it up over here. These are your hybrids, trigonal planar. What else is on this carbon? P orbital. P orbital is like this. Not hybrid, it's just a plain P orbital. Got one electron, and these are interacting side to side. This is your pi bond. The interaction is above and below this here, the nucleus. Okay. Between the 2 carbons, a sigma bond, head-to-head overlap of the hybrids, and then the pi bond, side-to-side overlap of the p orbitals on each atom. You finish this up over here. This is the same exact thing. Side-to-side overlap is not head-to-head, but side-to-side. And so they interact side-to-side. And the interaction, if the nucleus was in the middle, the interaction is both above my finger and below, right? Half of it is above, half of it is below. But that's only one bond though, right? All that is the pi bond, one pi bond in there. Can you rotate this? I don't have it set up, but you can't, because if I turn this, it may be still touching. It's no longer bonded. It has to be full side-to-side overlap. And so it's not going to want to do that and spin. Okay? On the other hand, this one will. Because it's only a head-to-head overlap, and it will allow for spin. All right? The bonding is very mechanical, just like this. Okay? Just like balloon spreading now. It's nature. We just can't see it. But it acts a lot the same. Until you get to quantum chemistry, where it doesn't quite act the same. Right? And it confuses people, and you just have to say, I think we understand. Okay, what do we have here? Questions? Bond angles here. What is this bond angle here? Any bond angle for trigonal planar? 120, right? 120? 120? Yeah? All the way around? Planar, pi bond. One electron from carbon interacting with one electron from carbon. Of course, orbitals interacting, because electrons are described by orbitals. Okay, we're not going to be able to do SP today. We'll do that next time. Questions as we close? Bond lengths and bond strengths, very important. Table 1.2, that's in this handout. Fine. Other hybridization. No, it's not in that handout, it's in the white handout. The white? Yeah, DUS on the back there. Very important on the back. We'll be hitting that next time. Have a good day, guys.